Yeah, that's sadly a possible reality. But anyway, at least so one of the if you have seen any Kevin Buzzard talk, he admits this and he says that even if can't be right. Yeah, yeah, sure. You can write in VS Code just that. I mean, you need to set up lean for VS Code on your local machine, and you might need to copy down the problem statements. Right. So you guys can see my screen, right?
Yes.
Cool. So just I'll send the link in the chat again. Okay. So at least so for the first few levels, we will be doing very basic stuff since you need to have some familiarity with the syntaxes. So at least the first four mini games will be boring, but yeah, bear with me. Uh, right. So I hope so. If you want to work on the web version, make sure that you have this thing here, which just tells you what to want to put, and this thing here, which tells you the errors. Right. So in Lean, basically, like Haskell, every variable has a type, right? Every variable has a type, and then functions have a type, and so on. So, is there a lot of background noise?
Yes.
Sorry. Uh, look, so you, yes, Lucky Puja noise. So you can still hear me, right? I mean,
Yes. Yes.
it is a, if it is a big problem, we can wait 5 10 minutes. It should be over. Cool.
Not a
So
big problem.
nice. So one more thing is, so there is at least for some of you, a lot of syntax will be new. So if at any point you want me to go back anywhere and you want to ask me what this syntax means or what this tactic means, feel free to do so because I don't expect you to memorize all this in short while. Anyway, so uh, you can see on the top right of my screen you have written there is written XYZ minat and uh, rotated t and some condition or some equality. Right? So everything above the rotated t is the thing that we are given. Right? So this basically says that XYZ are elements of the type minor, which here just means natural numbers. And everything after the t is something which we have to prove. Nice. Uh, so, the, so in lean there won't be any traditional functions, and instead we will call those things tactics. So also yeah, I if you can read like however much of this intro you can. So so the first tactic we will learn is very basic. It's called REFL, short for reflexivity, and so here's the code. So REFL basically REFL if you have two things which are equal by definition, you can solve that by using the tactic referral. And in lean, every line of your code must end with a comma, right? So for those of you who have your computers were able to, so were able to finish the level. I
Yeah.
mean, this is very basic. Nice. So anyone that has any issue, because sometimes the only thing that comes on the top right window is lean is busy. Okay, I hope no one has any problems. I'll move on to the next level. So the first four levels will be very basic tactics, just to introduce you. Right. The next one is something called the rewrite. So again, you have this is your given information, that is xy is minor natural numbers, and this is a hypothesis that y equal to x plus 7, and we want to show that 2 star y is equal to 2 star x plus 7. Right. So the tactic for this is RW or rewrite, which so I have to give RW and then the hypothesis. So you see that the goal changed. The goal here was 2 star y equal to 2 star x plus 7. We used h, and now this is 2 star x plus 7 equal to 2 star x plus 7. Now, can someone quickly tell me how to finish this?
Referral with the comma.
Reflexive.
One guy said, so Gautam, did you say something else? Or?
No, I think both of us said referral. I said with the comma at the end of it.
So referral works. One more thing, one more way in which you can use RW is, so note that we replaced y by x plus 7 and not the other way. But ideally, you should be able to do both, right? So to do that,
So what is the
you
H
type a
indicator
slash.
here?
L is that hypothesis.
Okay.
Is that hypothesis y equal to x plus 7. So to do the other way, you see now we have 2 star y equal to 2 star y instead of 2 star x plus 7 equal to 2 star x plus 7. And again, the referral finishes. Right. So anything you want to ask me?
Yeah. So RW rewrite, what it's doing is you have the hypothesis and it replaces every occurrence of it would replace every occurrence of y with x plus 7. Is that correct?
Not every occurrence. It might sometimes happen. So sometimes it happens is in your equation there are some occurrences you don't want to replace. So you can, I think if I remember correctly, RW replaces only one occurrence in your entire the thing you want. Right.
Okay.
And the difference between RW and RW slash L.
Okay.
Right. So should I move on?
Yeah.
Cool. So okay. If you have studied, or even if you haven't studied piano axioms, so piano axioms is the piano axioms is sort of the at least one of the formal ways you can define a natural number. You can define the set of natural numbers, and one of the things that comes up in your piano axiom is a function called SUCC. I think you have done this in Haskell as well, the successor function, right? So right now we don't have much any property of the successor function. We just know that it is some function. We don't even know, for example, that successor of a is same as a plus 1, right? So okay, someone tell me the solution.
RW of success of A or actually, sorry, H, right? Yeah, sorry, RWH. And then you can do the reflexivity.
Nice. So one more thing, one more quick trick. Of very often you have these problems that the last step is RW and then reflexivity. You can change that by just writing RWA, and that automatically finishes all of it. Cool. So RWA works. I think. Yeah, go on.
Yeah, the comma is like a semicolon kind of thing. You have to put it after every line.
Yeah. Not every line, but you might have some multi-line statements, but yeah, you use it the same way as the semicolon in C++. So I think RW slash L should also work. Yeah, it works. Cool. So I think I can move on. Okay, so here's our first. Here's our first. So we are, in some sense, trying to define the natural numbers. So if you can, I think here, yeah. So on your right, on your left, you have these things, and these tell you that what are the hypotheses that you can already use. So I can use add zero, and I can use add successor. I don't think I can use add successor. I'm actually proving add successor. Is it? Okay, so Anna, I can use both. I can use both add zero and add successor, and I have to prove add successor zero. So again, someone tell me a proof. So I hope these things are clear, that which one is the hypothesis, which one is a statement, which is a hypothesis name, and so on. So we have these two properties, right? These two hypotheses, a plus 0 equal to a, and a plus successor of b equal to successor of a plus b. We want to show that a plus successor of 0 equal to successor of a. For people who just joined, do you want me to, I mean, in some of you might have finished the first level by your first tutorial word by yourself, but for people who just joined, do you want me to repeat anything? I mean, the things that I've done here so far.
Yeah, I'm sorry, I just joined right now. Like, I have no idea what's going on.
Yeah, so, okay.
I'm sorry
Yeah,
if.
yes, thanks. So, you have the link to the game, right? Should I resend?
Uh,
Yeah, thanks. So people who just joined, you can open the, you are able to open the link, right?
yeah,
Should
yeah.
I?
Yeah.
Nice. So in Lean, similar to Haskell, you have variables, and variables have types. Functions also we'll call variables only. So you see on the top right side, we have something written, and everything above this rotated T is the given hypothesis, or is the information we are given. This just says that x, y, z are natural numbers, and everything after the rotated T is the thing we want to prove. Cool. So in Lean, to prove things, we use so the proper name for the literal token is tactic. So we will use tactics. So the first tactic you will learn is called the referral tactic, which is short for reflexivity. So you just type referral and you put a, in Lean you should end every line with a comma. And what Referral does is, if you have A equal to B and A and B are definitionally equivalent, like they are the same by definition, there is no need of substitution or anything, no cleverness needed, then Referral will just close the proof and yeah. So was that clear for people who just joined? So I can repeat it. I can repeat anything if you want to. Oh, they already like said. So for people who just joined, was that explanation of Referral clear? Proved up?
I'm not exactly sure, like what's, yeah. It's I'm
So
not yeah, like it's just it's just all sudden, so I'm not very clear about like this.
so you got what we want to prove, right? What the given information is and what we want to prove.
Yeah.
Right. So we want to prove that xy plus z, x star y plus z is same as x star y plus z. So to prove this, you have in normal programming languages you have these functions and variables and so on. Here we can use tactics. So the tactic we use is called the Referral Tactic. And so what 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 do you have problem in? What is the issue?
Um, yeah, what exactly is REFL again?
Referral is short for reflexivity. So
Okay.
if you want to prove, if your proof statement is A equal to A, then you can finish it by referral. You can finish your proof by referral.
And what does it do? Exactly, I mean, how does it look like?
So you have to. So your proof statement is of this form, right? I don't think I understood what your question was.
It's okay, I think I'm getting it.
So
Yeah.
so even if you aren't, I think with some more experience you will with some more levels. So
Yeah.
basically, referral closes everything that is definitionally equivalent. Then the next thing I want you to show is right. So here again we have x, y are the variables which are of the type minor, which just means natural numbers, and we have a hypothesis h which states that y equal to x plus 7, and we want to show that 2 star y is equal to 2 star y is equal to 2 star x plus 7. So you see, we cannot finish by referral. So if we type referral, it shows an error. So what that tells you is there is some sort of cleverness involved, and that cleverness is that we have to use the given hypothesis H. So what we can do is to use the hypothesis H. The syntax is RWH, which means rewrite H. What it exactly does is that you're asking y equal to x plus 7. So RWH will look for the first time y appears in your proof, in the thing you want to prove, and will replace that by x plus 7. Now can Rohtak tell me how to finish? Or
Um,
anyone? Yeah, sure. Go ahead.
oh no, I'm not sure.
Ah. So you understood what RW does, yeah?
Yeah, it just rewrites I mean,
Yeah. So now we want to prove that 2 star x plus 7 and 2 star x plus 7 are equal. So you see, you have two things which are definitionally equivalent, right? So the REFL will kill the proof.
Okay.
So okay, this you can tell me what to do. Let me. Cool. So can someone who just joined a few minutes tell me a proof? Anyone? I don't really want to call a specific person.
RW add of sub, then RW add 0, then refer.
Oh, you were talking about level 4, right? I'm on level 3. So can someone who joined in the last 5-10 minutes tell me a proof? Or is it too easy to? So if you have anything you want to ask about what the statement says, feel free to ask.
Arindam, sorry, did you ask a question? I couldn't hear you clearly enough.
So I was saying that can someone tell me a proof of this?
Okay, for this, the thing on the screen,
Yeah.
maybe the first thing to do is our assumption is a succession of A is B, right? So maybe we can write RWH, comma, and then since RW will replace this, what is it called? Successor of A with B, both sides have the same thing, right? So we'll just use the reflexivity. So REF will come.
Nice. So was that clear for everyone? Anyone? Should I move on?
Yes.
Cool. So yeah. So here is what we want to prove. We want to we are given that A is a natural number, and we want to show that A plus successor of 0 equal to successor of A. But sadly, we don't have too many properties of natural numbers yet. We are kind of trying to define the natural numbers, and the only properties we have is that this thing on my left, A plus 0 equal to 0, and A plus successor of B equal to successor of A plus B. So what should be the first step in the proof?
Arindam, could you wait for 1 second? Like, let us read the instructions they've given over here.
Yeah, sure. Yeah.
Can I give a proof now, or do we wait?
So tell me the first step of the proof, and then someone else can finish.
Okay. we say add successors of we say sorry we RW add successor.
Will that work?
One second. Add successor of x and 0. I'm not sure. Like the syntax.
Yeah, I mean it works. It works.
Oh, okay.
So you see that the thing we want to prove has changed
Yeah, and then
from a plus successor of 0 equal to successor.
yeah,
Yeah, can someone else finish?
sorry.
So can someone else finish the proof? You can even type in the chat if you.
Then RW add underscore 0.
RW add 0.
Yeah. And then reflexivity.
So this was clear, right?
Do we
Anyone
need
has
to
any doubt?
do we need to do RW add 0?
So what else do you suggest?
We just remove. We
I
just
mean,
do R. Sorry.
go on, go on.
You just commented out RW add 0, right?
Yeah.
So, like my proof was RW add successor, comma reflexivity, and then it just showed a proof complete. So I'm asking why do we need to do RW add 0?
Right. So the thing is, reflexivity. So this is important. Reflexivity finishes proof if and only if the two things on the left and the right are definitionally equivalent, right?
Okay.
So
Yeah.
the thing is, a plus 0, computer already sees a plus 0 as a, even
Okay.
though that is one of our hypotheses, but for the computer, anyway, for the computer, a plus 0 is defined as a.
Yeah.
So computer does not understand what a plus 0 is. Computer understands that a plus 0 is.
Okay. So what you're trying to say is
Right.
that RW, if we don't do RW add 0, the left hand side is successor of a plus 0. But the computer already knows that a plus 0 is a, and so directly doing REFL works. But uh, uh, conventionally, we are supposed to convert a plus 0 to a, and that's why we need RW add 0.
Yeah, exactly.
Okay, cool.
Nice. So I'll wait uh, 2 minutes for if anyone has any doubt, because so what we are doing so far is just kind of syntax. So anyway, any doubts?
So if I've been understanding this right, it's what rewrite is doing is it's going to find the first instance of the pattern which is sort of defined in the proof of add 0, and then it's going to replace the first occurrence of that pattern with whatever add 0 proves.
Exactly.
Okay, yeah, that's what I wanted to clarify. Thanks.
Nice. So I guess I'll move on, but uh, yeah, feel free to ask me any of the syntax or anything at any point. So the next thing is addition rule. So yeah. So I'll give you a few minutes to read the introduction because we will need a new tactic. So whenever someone has read the thing, feel free to tell me what the first line of the proof should be. So feel free to ask me if you have any doubts in the thing that they have written in the introduction. I am audible, right?
Yes, I didn't have any doubts.
Nice. So can someone tell me what the first line should be?
Induction N with DHT.
Right. So what this does is we are basically inducting on n, but since we are saying the variable is not n, we can also keep induction n with n hd. But anyway, so d is the variable we are inducting on, and hd will tell us what the induction hypothesis is when we are trying to go from d to successor of d. Right? So you see now we have, instead of one goal, we have two goals here, and the way lean works is we have to finish the goals one by one. So first we need to do this, then we need to do this. Right. So is the induction tactic clear for everyone? Uh, you can just type a yes in the chat.
So the variable can be named anything, right? This DHD, we can even name it like FX or something, anything.
Yeah. So the first thing will be the variable name. So the second thing will be the name of the hypothesis, and you can give any names. I think you can give any names other than like the keywords. Okay. So at least, so if you understood what induction does, type a yes in the chat. Then I'll move on to the next. I hope people are not asleep, although I won't blame them. So anyone wants me to explain what induction is, or okay, cool. So can someone other than the person who just said the first line tell me what the second line should be? Second line of the proof, I mean. We want to show that 0 plus 0 equal to 0.
You just use the add zero tactic and then like RWA add zero.
So add 0 is a hypothesis, not a tactic.
Oh, sorry. Yeah, the hypothesis, my bad. Your tactic you should be RWA add zero. No, I meant RWA add zero. So like you don't even need to type REFL after that, right? So yeah. And now you just have to use add suck and then like RW add suck and then RW HD after that.
Nice. So should I move on?
What's RWA?
Anyone who wants me to explain this?
I didn't.
So RWA does both RW and RFL.
Oh, okay.
Sorry, it does what? RW and?
RFL.
Okay, okay.
So I think, okay, I guess I'll move on. Okay, this will be a slightly bigger one. So first thing, note that by definition, this bracketing thing for lean is the right associative rate. So here it won't say that it is actually doing a plus b first and then adding its. So feel free to tell me what the first line should be once you have read it.
Arindam, sorry to take you back a little bit, but could you? I didn't understand the induction. I don't well enough.
So any particular part about induction?
Like the first part, like what are we doing? I didn't get that.
So we want to prove that 0 plus n is equal to n, right?
Yeah.
But we have proved that n plus 0 equal to n, but to prove so that 0 plus n is equal to n plus 0 is not something we have done. We don't have commutativity yet. So the way we want to show this is we want to induct on n, and the syntax for this is induction, the thing you want to induct on, the variable you want to call it, and the name of the induction hypothesis. So here you see there are, so whenever you induct, at least in lean and the way natural numbers are defined, the first step is to show it for 0, and so the base case is always 0, although you can change it sometimes, but you won't need it in this game. So the base case is 0, and then you assume it is true for some d, and you want to show that it is true for successor of d.
Okay. So here I got the first line. Yeah, I got the first line of the syntax, and then how do we move on to the base case? Like, how do we show the base case?
We just add 0.
Oh, okay. So the second line, which is RWA add 0, is this is the base case.
Yeah.
Okay. Okay. And what is adds RW add successor? I didn't get that.
So after RW add 0, we have, you can see the current state of the goal here. We have the natural number, HD.
Yeah. Oh, okay, got it. Okay, makes sense.
Cool. So anything else?
No, I think that's it.
Nice. Okay, here. We want to show that addition is associated. So any idea what the first line should be? We have to induct on something, but we can induct on either A or B or C.
I got one. Induction C with NHN. And then RW add 0 twice. And then reflexivity.
So the base case is done.
Then RW add successor thrice.
Thrice.
For each. Yeah. And then RWHN. And refill.
So if I think I can automate this. If I remember lean, hopefully. Yeah, nice. So if you do repeat RW add successor, it will do it as long as it can no longer do it. Another thing I think I wanted to show is that. So yeah, let's see. So you see what it does, right? Because by itself, add successor will change anytime it finds a pattern which is of the form add successor. And if you want to do it on very specific variables, let's say b and n, so you have to tell it RW add successor bn. Right? You see, this thing is also in the same format: hypothesis name and then the variables on which the hypothesis is defined. Right. So was that clear?
Could you repeat that, please? The add set bn.
Right. So what RW does is, so what RW adds up will do is it will find the first occurrence of a pattern which looks like adds up, and you know,
Yeah.
it will find the first occurrence of a pattern that looks like this, the left hand side of adds up, and replace it by a pattern that looks like the right hand side of this. But often you want to do add suck on maybe not the first time you see the pattern, but something else, in which case you can specify the variables you want to add suck on. So what this does is this does b plus suck of n is equal to suck of b plus n.
Okay. And what is the repeat line?
Even this, yeah, just a sec. I think even this works. So if you do not want to, let's say, give an explicit variable, you can just type underscore and lean with figure out what to put there. What repeat does is, so the proof Advik said originally had RW add successor 3 times. So instead of doing that, you can just do repeat RW add successor.
Why do we need to repeat this?
We don't need to. We can just, so if we don't repeat this, we will have to type it quite a few times here. So
No, like in the proof only, why do you have to keep doing this again and again?
no, because we are actually applying add sub again and again, right? Even if you do the proof by hand, you are actually applying add sub again and again, right? Or did I not understand your question?
I think I didn't understand the initial step itself.
So can you tell me the line number?
I'm not getting if what I'm trying to ask is why do we why are we repeating that line again and again? Like in the base case also we've done RW add 0.
Because the first add 0 only gives you this mistake. One add W only changes one thing. You had a plus b plus 0 equal to a plus b plus 0. The first thing just, you see, it found the first occurrence of the pattern for add 0.
Okay.
Right? So what this does exactly is,
Okay.
this is what it's doing, right? It's applying add 0 on the variable a plus b.
Okay.
But then I want to do it again on,
B plus 0.
I will have to do this.
Okay. Okay. So we're getting because
Also,
okay. So
no,
we're
it does not.
So if you do this repetition, because C has two instances in the hypothesis, so to replace each of those in the base case, or in the induction step, we have to do it twice. Is that what you're trying to say?
Sure, that's one way to look at it.
Okay. Okay. Okay, got it. Thanks. So in the base case also, we can just write.
Yeah. We can just do repeat RW.
Okay.
So can someone tell me which variables exactly are we doing the add work on here? The second one. The first one we did on B and N. The second one. Yeah, go on.
It's B and N again, right? On the left hand side.
On the right hand side, I think, right?
But left hand side you don't have. On the right hand side, yeah. No, even on the right hand side you are not doing successor of B and N, right? Successor of B and N on left hand side, you mean?
Yeah, on
the left hand side.
The B plus suck N will become suck of B plus N.
So the thing is, it does not show this, but this actually is A plus B within the bracket,
Okay.
and then successor of N.
Okay. In that case, you would do it on A plus B and N.
Exactly. And the final one?
A plus suck of B plus N. So A and B plus N. Okay.
Not plus, right?
Yeah.
Yeah. Awesome. Then we apply the induction hypothesis and refer. Cool.
Could you wait a minute here?
Is this clear? Should I?
Just wait 1 second.
Yeah, sure.
So in the previous proofs, the reason we didn't have to say which things we were rewriting is because there was only one thing to rewrite, right?
So if you don't say anything, it will just find the first occurrence of that pattern and do it itself.
Okay.
So this is one of the strong points of type theory, right? even in Haskell, you have that Haskell can do these kind of things. You can, I don't know if you have seen it in your course yet, but you often don't need to specify what exactly you are working on, but Haskell will do it. So I don't think I will go to level 3. I wanted to talk about something else and something else related to lean, and I'll so once this level is done, we'll move on to that.
Okay, could you just scroll up a little bit? I think I'm having an issue with my code. I just need to cross it. Thanks.
So tell me when you're done, or if you have a specific debugging issue.
No, I think I'm done.
Cool. So yeah, the thing I actually wanted to talk about was, let's see where. Okay. So so I'm skipping ahead, but I hope things will be clear, or they will be clear once you maybe do it yourself. So what this says is that P and Q are variables of type, which for now you can think of as that P and Q are sets, and small p is an element of capital P, and h is a function from P to Q. And the thing we want to prove is Q, which means that we want to show the existence of an element in Q. So repeating again, I have a function from P to Q. I have an element of P. I want to show that there exists an element of Q. So what's the, not the lean way, what's the natural way to do this?
We have P is an element of P, and because it's a function, h of P has to be defined, and so that is an element of Q.
Exactly. So the way to do this in lean is exact h of P. So even if I have like some more complicated, not this one maybe, yeah, sure, maybe this one. So you see I have a bunch of functions and I want to prove something. So the exact thing is not important for now. The type of the thing, the kind of thing we are doing is that we have a element of a set, we have a bunch of functions, and we want to show that some other set is non-empty, right? So here's the thing. There is a very natural way so now we have almost everything is same, but instead we have PQ propositions. That is to say that PQ are some statements, and small p, instead of small p being an element of the set P, we have that small p is a proof of the proposition, and we have a function h which can transfer any proof which you give input a proof of P, and it gives you a proof of Q back. Right. or basically you can think of it as H says that P implies Q. So we have that small p is a proof of P, and we have the hypothesis that P implies Q, and we want to show that Q is true. So you see that this is very similar to that case set, but instead of sets and elements, we have propositions and their proofs. At least that some form of equivalence is clear, right? That there is something going on here.
Yeah.
Am I audible?
Yeah.
Yeah.
Yeah. So you see that there are a lot of similarities between these two programs.
Yeah.
Their proof is the same, the way you do it in Lean, but what this actually leads to is that
Arindam, your voice is distorted.
Is this better?
Yeah, this is better.
Cool. So I'm saying that there is a lot of equivalence going on here, right? And in some sense, this equivalence is what started the field of type theory. So can you see my? You can't see my Google screen here. You can see my screen, right?
Yeah.
So this form of isomorphism that you had between mathematical proofs and computer programs actually kind of started the theory of the field of type theory, and then from type theory you have all this Haskell and everything. So the thing I wanted to end the session on is that this thing called the Curry-Howard isomorphism, Curry-Howard correspondence. Yeah, that's all I wanted.
Thanks. That was very interesting.
Any doubt? Or any?
So will we be having more of these? Or?
I can have more of this, but I mean, it depends on business. Depends on when I'm free. So, how many of you want more of this? If like 5, 10, or 2, 3 people want, I can do it. If
More of this
more than
hasn't
one
Lean,
person
right?
wants it.
Yeah, the
Yeah.
Yeah.
I mean, the game you can also finish by yourself.
yeah, but yeah.
So you can finish the game by yourself, and then so you can actually do groups, subgroups, whatever you are learning in real analysis. Almost everything you can do in Lean, you can do a proof in Lean. And yeah, if you want specific resources to see that, you can DM me, or I'll just send you a mail. But yeah, that's up. Anything anyone wants to say? No.
Could you show us the proof for like this level that you were playing, the proposition world level 1? It's like the same thing, right? Exact h of p, and then
Yeah, the same thing works, but there are also other ways to prove it.
oh, okay.
Yeah, but those ways are basically the same.
Okay.
Cool. I'll then end the session.
Yeah, thanks for the session.
Thanks. It was great.